Bismillahirrahmanirrahim. Menghadap Duli Yang Teramat Mulia Raja Muda Perak Darul Rizwan Raja Nazrin Shah selaku pengerusi kehormat Bridges Malaysia, dan Duli Yang Teramat Mulia Raja Puan Besar Perak Darul Rizwan Tuanku Zara Salim. Ampun Tuanku, beribu-ribu ampun, sembah patik, mohon diampun. Patik bagi pihak penganjur acara dan juga para hadirin sekalian mengalu-alukan keberangkatan duli-duli tuanku mencemar duli ke majlis Bridges Dialogues Towards a Culture of Peace ini. Ampun tuanku. Sesungguhnya keberangkatan duli-duli tuanku merupakan penghormatan besar bagi patik sekalian dan tidak akan dilupakan. Ampun tuanku, patik memohon limpah perkenan duli-duli tuanku untuk memulakan majlis dan seterusnya berucap dalam bahasa Inggeris. Ampun tuanku. Your Royal Highness, the Crown Prince of Perak Darul Rizwan, Raja Nazrin Shah, Ibni Sultan Azlan Muhyiddin Shah, the Malaysian Honorary Chairman of Bridges, and Your Royal Highness, Tuanku Zara Salim. Yang amat berbahagia, Tun Dr. Siti Hasmah Haji Muhammad Ali. Yang berbahagia, Tan Sri Samsudin Osman, Presiden Perbadanan Putrajaya. Yang berbahagia, Datuk Syaril Samsudin, Honorary Treasurer Perdana Leadership Foundation. Mr. Uwe Morawetz, Chairman of the International Peace Foundation. Professor George F. Smoot, 2006 Nobel Laureate in Physics. Distinguished guests, members of the media, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon and a warm and slightly wet welcome to today's talk, Contemplating the Birth of the Universe. You know what they say, into each life some rain must fall, but that's okay because we're all here to build bridges. Today's talk is part of the Bridges Dialogues Towards a Culture of Peace program initiated by the International Peace Foundation. As we have an interesting afternoon ahead, without further ado, it gives me great pleasure to call upon Yang Berbahagia Datuk Syaril Samsudin, Honorary Treasurer, Perdana Leadership Foundation, to deliver the welcome address. Dipersilakan, Datuk.
Assalamualaikum warahmatullahi wabarakatuh, and good afternoon. Tuan-tuanku, His Royal Highness, the Crown Prince of Perak Darul Rizwan, Raja Nazrin Shah, Ibni Sultan Azlan Muhyiddin Shah, Honorary Chairman of Bridges Malaysia, Her Royal Highness, Raja Puan Besar Perak Darul Rizwan, Tuanku Zara Salim. Yang amat berbahagia, Tun Dr. Siti Hasmah binti Haji Muhammad Ali. Yang berbahagia, Tan Sri Samsudin Osman, Presiden Perbadanan Putrajaya. Distinguished guests, members of the media, ladies and gentlemen. On behalf of the Perdana Leadership Foundation and Perbadanan Putrajaya, it gives me great pleasure to welcome you today to the Bridges event, a talk by Professor George F. Smoot. May I also extend our deepest appreciation to their Royal Highnesses, Raja Nazrin Shah and Tuanku Zara, for gracing our event today. Your Highness, thank you for honoring us with your presence. Your Highness, ladies and gentlemen, this is the second time that the Perdana Leadership Foundation is hosting a program under the Bridges umbrella. And today we are pleased to welcome Professor George Smoot, 2006 Nobel Laureate in Physics, as our keynote speaker. Our first program in December last year focused on economics, with Professor Dr. Robert Engel presenting his theory on the causes of the financial market volatility. Today, however, we will have our attention drawn away a little further from home and instead be directed towards the heavens as Professor Smoot shares his thought and discoveries on the origins of our universe. I believe today's talk will be a most interesting one as we will gain a peek and some clues into God's creation, the universe. On behalf of the Perdana Leadership Foundation, I would like to thank Tan Sri, Samsudin and Perbadanan Putrajaya for providing us this exquisite venue for today's talk. I must, of course, thank Mr. Morawetz and the International Peace Foundation for bringing the Bridges program to Malaysia. It presents a wonderful opportunity for Malaysians to listen to luminaries from a diverse field of studies, which will provide inspiration to us all. Last but not least, I thank the hard-working committee members of both the Perdana Leadership Foundation and the leadership of Tan Sri Nik and the Perdana Perbadanan Putrajaya for their efforts into making this event a success. Your Highness, ladies and gentlemen, you have come today to listen to the 2006 Nobel Laureate in Physics. Let me therefore once again thank you all for being here today and make way for today's proceedings. Thank you. Ampun Tuanku.
Thank you, Yang Berbahagia Datuk. And now here's the chairman of the International Peace Foundation, Mr. Uwe Morawetz, to give you an overview of Bridges. If you please, Mr. Morawetz.
Your Royal Highness Raja Nasrin Shah, Your Royal Highness Tuanka Zara Salim, Tun Dr. Siti Hasma Muhammad Ali, Tan Sri Samsudin Osman, Excellencies, ladies and gentlemen, friends. Welcome to the second ASEAN event series Bridges, Dialogues Towards a Culture of Peace. Bridges is facilitated by the International Peace Foundation, a non-political and non-religious foundation under the common patronage of 21 Nobel Peace Prize laureates based in Vienna. The events are hosted in cooperation with various local partners, including some of the country's major universities and think tanks, and I would like to thank the Perdana Leadership Foundation for hosting our event today. Having started in November 2008, Bridges is being continuously held in Malaysia and Thailand until April this year, involving the participation of Nobel laureates for peace, physics, chemistry, medicine, and economics. The second ASEAN series of Bridges is an independent contribution to the Decade for Culture of Peace and Nonviolence, which was initiated and promoted by the United Nations General Assembly. It follows the Bridges series, which the International Peace Foundation has already hosted in Thailand and the Philippines since 2003. The pluralistic program of Bridges highlights the International Peace Foundation's intercultural and transdisciplinary approach towards peace. The foundation doesn't take sides, but acts as a mediator by creating an independent platform for dialogue, where representatives of science, politics, economy, culture, religion, the media, and youth can meet, share their viewpoints, listen to each other, and find mutual ways of understanding and cooperation. Therefore, the Foundation itself is a bridge and a facilitator between different language groups in our divided societies, where politicians speak another language than artists, and business and political leaders another one than scientists. In a highly interdependent world, problems cannot be solved by either one of these language groups only, but by finding ways of working together. After the success of its bridges programs in Thailand and the Philippines, the International Peace Foundation has been invited by other ASEAN countries to build further bridges towards peace and international understanding by expanding its program in Southeast Asia to stimulate the intellectual, scientific, and cultural exchange in the region. The aim of bridges is to facilitate and strengthen dialogue and communication between societies in Southeast Asia with their multiple cultures and faiths, as well as with peoples in other parts of the world, to promote understanding and trust. The events aim at building bridges through Nobel laureates with local universities and other institutions in Southeast Asia to establish long-term relationships which may result in common research programs and other forms of collaboration. By enhancing science, technology, and education as a basis for peace and development, the events may lead to a better cooperation for the advancement of peace, freedom, and security in the region with the active involvement of ASEAN's future, the young generation. This is why Bridges is not designed as a one-time event, but as a continuing process of synergies to make the series of events a sustainable success for Malaysia and for Southeast Asia as a whole. I'm grateful to the Malaysian Honorary Chairman of Bridges, His Royal Highness Raja Nasrin Shah, and to our Chairman Tun Musa Hitam. Their powerful guidance paved the way for Bridges to bear fruit. I'm also grateful to the representatives of our local partner institutions who have developed the detailed schedule of events in continuous meetings, as well as to our sponsors who have enabled us to make the idea of Bridges a reality. I would like to say thank you to everyone present today for taking part in this program. May it help us to facilitate a new culture of peace through dialogue, transcending its definition as merely the absence of war or armed conflict into a new understanding what the basis for peace is: education. In this spirit, we welcome today Professor George Smoot, the 2006 Nobel Laureate for Physics, who has agreed to come to Malaysia to support the events. We all look forward to his keynote speech and to his important contribution to build bridges. Thank you very much.
Thank you. Thank you, Mr. Morawetz. Ladies and gentlemen, moving on in today's program, I'd now like to call upon Yang Bahagia Tan Sri Samsudin Osman, President Perbadanan Putrajaya, to provide a background to Putrajaya. Silakan Tan Sri.
Ampun tuanku. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Royal Highness the Crown Prince of Perak Darul Rizwan, Raja Nazrin Shah, Ibn Sultan Azlan Muhibbuddin Shah, the Honorary Chairman of Bridges Malaysia, Your Royal Highness Raja Puan Besar Perak Darul Rizwan, Tuanku Zara Salim Davidson, Yang Amat Bahagia Tun Dr. Siti Hasmah Binti Haji Muhammad Ali, Bahagia Datuk Syarif Samsudin, Honorary Treasurer, Perdana Leadership Foundation, Mr. Uwe Morawetz, Chairman of the International Peace Foundation, Bahagia Tan Sri Nik Muhammad Nik Yaakob, Executive Director, Perdana Leadership Foundation, and Bahagia Tan Sri Datuk Dr. Umar Abdul Rahman, President and CEO of the Malaysian University of Science and Technology, Professor George F. Smoot, 2006 Nobel Laureate in Physics, distinguished guests, members of the media, ladies and gentlemen. Let me bid you selamat datang, or a very warm welcome to Putrajaya, the Federal Government Administrative Center. We are honored to co-host with Perdana Leadership Foundation this prestigious Bridges program for the second time. Ladies and gentlemen, it's my pleasant duty now to say a few words about this beautiful city of Putrajaya,
more for the benefit of Professor, this is first time for him, and for those fellow Malaysians who have not discovered the beauty of Putrajaya. Putrajaya, which was specially planned and developed to be the federal government administrative center of Malaysia. It was first conceived in the 80s when the Malaysian government sought to relieve the pressure from Kuala Lumpur's overstretched infrastructure and create a new working environment for its civil servant. The planners conceptualized a city in a garden where the country's leaders and administrators will be able to live and work in surroundings conducive to inspiring fresh ideas for a better Malaysia in the 21st century. Development of the city in earnest started in the mid-1990s, and it marked a new chapter in the development history of modern Malaysia, for it was to be our largest ever integrated urban development project. Putrajaya was planned to grow into a self-contained urban center, which, besides accommodating government ministries and agencies, would also include components such as commercial, education, diplomatic missions, tourism, convention center, and regional or institutional headquarters. The city sits on a magnificent 4,931 hectares of land, where office buildings and houses are surrounded by gardens and parks, which was once filled with rubber trees and oil palms. With a current population of almost 50,000, Putrajaya is not just turning into a vibrant community, but the city has built a reputation for being a tourist destination and a must-visit place for foreign dignitaries. About 2 million square meters of government office space has already been completed in Putrajaya. A total of 20 federal government ministries and 51 government departments, as well as agencies, have already moved into the city. It is targeted that by 2010, all government ministries and agencies that are scheduled to migrate to Putrajaya will have moved in. Having achieved that, our efforts are now focused on bringing in private sector business and investment to the city. This has shown encouraging results. Some commercial plots within this town center are now being developed for commercial and office complexes by local as well as foreign investors. The impressive Putrajaya Boulevard, which is the center spine for the city, is planned to have a healthy mix of government and commercial buildings. The commercial plots have been planned to accommodate various activities such as offices, shops, high-end restaurants, cafes, and other retail outlets. Of course, all this might not come into being overnight, but the signs are there and it looks quite encouraging. Given more time, we should be able to witness the true extent of the commercial activities planned for the core island of Putrajaya and along the boulevard in particular. Ladies and gentlemen, a city conducive for work and play is one in which is livable and vibrant. Towards this end, Putrajaya Corporation has taken the lead in organizing events and programs in the city. In sports and recreation, the Putrajaya Lake in particular is being geared towards becoming the premier water sports center in the country, having hosted events such as the Asia Canoe Championship, the International Water Ski World Cup, and the Formula One Powerboat Championship. On the arts and cultural front, some of the more popular events include the Flora Fest, the International Fireworks Competition, and the Putrajaya Arts Festival. One of the greatest challenges in developing Putrajaya is to build a city that is identifiably Malaysian, reflecting the diverse cultures and traditions that we have in this country. This can be seen in the attractive ambience and impressive character of the buildings, bridges, and even down to the lighting poles and street furniture. It is this blend of the Eastern and Western design that I believe are drawing visitors and tourists alike to Putrajaya. An important aspect of development in Putrajaya is in the architectural lightings. Buildings in Putrajaya were lighted up at night, and this is achieved through carefully designed lightings carried out in accordance with the Putrajaya Lighting Master Plan. Therefore, when government and commercial buildings in Putrajaya are built, besides bringing in life to the city, they would also contribute to the beautiful nighttime ambience of the city. In so doing, they are able to attract more visitors to the city even after office hours. As a complete city with a balance in function activities, Putrajaya also boasts a diplomatic precinct which has been meticulously planned and well complemented with amenities such as a commercial center and an international school, a town square, as well as numerous parks. Designed specifically to meet the needs of the diplomatic community in Malaysia, the Putrajaya Diplomatic Precinct offers a total of 61 embassy lots for sale to foreign missions wishing to move to Putrajaya. To date, a total of 44 of these lots have already been sold. And being a garden city, one very important component of Putrajaya is the Putrajaya Lake. This 400 hectares man-made lake was meant to bring a certain character and create a unique image of for the city. In fact, Putrajaya would not be as beautiful without the lake. Together with the wetlands, it has been able to introduce a varied living experience and added another dimension to urban living, which is waterfront living. It has also brought nature into the urban fabric with the existence of wildlife, flora and fauna close to the urban population. The wetlands, which were also man-made, which serve as a filter for the stream feeding into the lake, have become a feeding area for migratory birds. Ladies and gentlemen, today Putrajaya is the pride of our nation. I dare say it's a vision realized. It would not be realized, however, without the vision, foresight, strong political will, single-mindedness, determination, and courage of our political leader at the time to make it happen. I refer to Yang Amat Bahagia Tun Dr. Mahathir Mohamad, Malaysia's 4th Prime Minister. Thank you, ladies and gentlemen. Ampun Tuanku.
Thank you, Tan Sri. Your Royal Highnesses, distinguished guests, the moderator for the talk today is no less a personage than Yang Berbahagia Tan Sri Datuk Dr. Omar Abdul Rahman. Now, Tan Sri's list of accomplishments and achievements runs to the pages, but in the interests of time, suffice to say that he was the first person to be appointed science advisor in the Prime Minister's Department in 1984. He served on various national committees in the areas of development, planning, scientific research and development, information technology, and telecommunications. Tan Sri is Senior Fellow and Founder, President of Academy Science Malaysia, and is now President and CEO of Malaysia University of Science and Technology, MUST. Now, ladies and gentlemen, many events promise you an exciting time, but it is only this talk that can offer you a big bang moment. Ladies and gentlemen, may I present your moderator for the talk contemplating the birth of the universe, Yang Berbahagia Tan Sri Datuk Dr. Omar Abdul Rahman, and our keynote speaker, Professor George Fitzgerald Smoot.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Your Royal Highness, the Crown Prince of Perak Darul Rizwan, Raja Nazrin Shah, the Honorary Chairman of Bridges Malaysia, Your Royal Highness Tuanku Zara Salim Davidson, Yang Amat Berbahagia Tun Dr. Siti Asmah bin Haji Muhammad Ali, Yang Amat Berbahagia Tun Dr. Ling Yosek, Yang Berbahagia Datuk Syahrir Samsudin, Honorary Treasurer Perdana Leadership Foundation, Yang Berbahagia Tan Sri Samsudin Osman, Presiden Perbadanan Putrajaya, Mr. Uwe Morawetz, Chairman of the International Peace Foundation, dan Yang Berbahagia Tan Sri Muhammad Ni Yaakob, Executive Director, Perdana Leadership Foundation. It is my pleasant duty this afternoon to introduce the Bridges keynote speaker, Professor George Fitzgerald Smoot, Nobel Laureate 2006 in Physics. And Professor Smoot will be talking on the topic of contemplating the birth of the universe. I must admit to having a lot of black holes translate that into deficiencies in my knowledge of astrophysics and cosmology. So therefore I look forward to the lecture. Maybe those black holes can somewhat, or a few of them can disappear. Our universe is said to be between 10 to 15 billion years. Now, if you can compute that, it's quite difficult to compute that kind of time frame. Or, in the language of cosmology, it is in the 10th cosmological decade. The possibility that the universe began as an explosive burst, first seriously suggested in 1920s, and the idea became dubbed as the Big Bang. About the same time, it came to be realized that if the dawn of the universe was indeed explosive, then a faint afterglow of this explosion might still remain and be detectable. In 1964, two scientists realized that the microwave background radiation flooding into their radio receivers was indeed such a signature of the Big Bang. Owing to the interference caused by the Earth's atmosphere, however, it was impossible to see this radiation unimpeded. In 1889, 15 years after it was first proposed, NASA's Cobe Satellite, Cobe meaning Cosmic Background Explorer Satellite, was launched to study cosmic microwave background radiation from orbit. Within minutes of starting its recordings, it confirmed that this diffuse radiation displayed precisely the expected frequency, wavelength relationship, the perfect black body spectrum predicted to result from first light in the universe. Here is where the work of our speaker today is of major significance to the Big Bang theory. Professor George Fitzgerald Smoot is director of the Berkeley Center for Cosmological Physics, who was awarded the 2006 Nobel Prize in Physics, along with Dr. John Mather, for the discovery of the black body form and minute variation of the cosmic microwave background radiation. In April 1992, Professor Smoot announced that the team he led had detected the long-sought variation in the early universe that had been observed by NASA's Cobe. And NASA's Cobe Satellite mapped the intensity of the cosmic background radiation from the early Big Bang and found variations so small, about 1 per 100,000, they had to be seeds on which gravity worked to grow the galaxies, or as well as clusters of galaxies and clusters of clusters that are observed in the universe today. These variations are also relics of creation. Essentially, Professor Smoot recorded the faint echoes of the birth of the universe. The precise satellite measurements of the cosmic background radiation confirm fundamental prediction arising from the Big Bang theory, leading to its further acceptance as the standard model of cosmology. The discovery, called the discovery of the century, if not of all time, by the famous astrophysicist Stephen Hawking, was the first step towards understanding the development of structures in the universe. Professor Smoot was born on February 20th, 1945 in Florida. His father, an engineer, was a hydrologist for the U.S. Geological Survey, and his mother was a science teacher and school principal. He studied at the Massachusetts Institute of Technology, where he earned Bachelor of Science degrees in Mathematics and Physics in 1966 and received his PhD in Physics in 1970. Although his doctoral thesis was on the decay of subatomic particles, Professor Smoot jumped to the field of cosmology for his research because he saw it was a frontier of fundamental science ripe for exploration. He is the author of more than 200 science papers and of the book called Wrinkles in Time that elucidate cosmology and the Cobe discovery. A professor of physics at the University of California at Berkeley, his honors include the NASA Medal for Exceptional Science Achievement, the Lawrence Award, and the Einstein Medal. Professor Smoot continues research in cosmology and is involved in the Planck and SNAP mission. The European Space Agency Planck mission is the third-generation mission to exploit the cosmic background microwave fluctuations discovered by Cobe. SNAP is a mission to understand the dark energy causing the current expansion of the universe to accelerate.
Energy contents of the universe. And we have these fundamental physics questions that we have to solve, but we know they're there. We know that there must be some answers to them. So, right, it's like we found the pyramid, but we only found the peak of the pyramid sticking out of the sand. We know there's a lot to excavate down and see. So it's really interesting and exciting for the next generation of things to do. So, namaste. Thank you very much.
In the context of the work of bridges, which is trying to bridge various gaps to establish peace. And if you look at the last few pictures on the screen that was shown to us, the billions of galaxies swirling around in space, and the galaxy in which we are in is only just one of them. And we are a planet, I don't know, one body among how many millions within our own galaxy. And within our planet, there are so many countries at conflict with one another. And then if you translate that to individuals, ourselves at conflict with so many others around us as well, that shows how the significance of it all. And if you look at that, there's no reason for us to be quarreling among ourselves as individuals, nations among nations, because we are so minute in the total concept. I thought that was the message that I get out of all this. Now, once again, Your Royal Highnesses, ladies and gentlemen, can we show our appreciation to the speaker?
Tagore says, where the mind is without fear and the head is held high, where knowledge is free, where the world has not been broken up into fragments, where words come out from the depth of truth into that heaven, let my country awake. I would now like to invite Yang Berbahagia Tan Sri Samsudin Osman, President of Perbadanan Putrajaya, on behalf of Perbadanan Putrajaya and the Perdana Leadership Foundation, to present gifts of appreciation to His Royal Highness the Crown Prince of Perak Darul Rizwan, Raja Nazrin Shah, as the Malaysian Honorary Chairman of Bridges. Dipersilakan. Yang Berbahagia Tan Sri would also be presenting token of appreciation to Yang Berbahagia Tun Dr. Siti Hasmah Haji Muhammad Ali. And a gift goes as well to Mr. Uwe Morawetz, Chairman of the International Peace Foundation. Tan Sri, if you could do the honors, please, to Mr. Uwe Morawetz, Chairman of the International Peace Foundation. Thank you, Tan Sri. I'd now like to invite Yang Berbahagia Datuk Sharif Shamsuddin, Honorary Treasurer, Perdana Leadership Foundation, to present tokens of appreciation on behalf of Perbadanan Putrajaya and Perdana Leadership Foundation to Professor George F. Smoot, 2006 Nobel Laureate in Physics. And not forgetting our able moderator for today, Yang Berbahagia Tan Sri Datuk Dr. Omar Abdul Rahman, President and CEO of Malaysia University of Science and Technology, MUST. Thank you, Yang Berbahagia Datuk.
Ladies and gentlemen, I now call upon Professor Smoot to come to the podium to deliver his lecture. Thank you, sir.
Salam, Your Royal Highnesses, honored guests, ladies and gentlemen. It's an honor and a pleasure for me to be here. And let me try and get this to start. It takes a second. And I will have to apologize for the first slide, because I should have said Putrajaya instead of Kuala Lumpur. And I know the difference. I'll fix it after the lecture. But I always had on my list to come to Kuala Lumpur because it sounded so exotic. But now that I know of Putrajaya, I should have put it on the list too. So I want to talk about contemplating the verse of the universe, but I want you to see how it is we actually dare to contemplate that and think that we can measure it and observe it and actually know what we're talking about. And so I thought the best analogy I could make is to CSI, the crime scene investigation, but this time a cosmic scene investigation. And so one of the things we do is we look around this room, and if we're true cosmologists, we can explain everything in this room, not in detail, but where all the elements came from that made up the things that are in this room, including me and the podium and everybody in the audience. So part of our goal is to explain everything in the universe. It's a mild goal, but that's what we want to do. Do I have a laser pointer? Oh, wait a minute. I found my briefcase. So we can do this. So I wanted to show you a picture of cosmologists at work. You can recognize they're cosmologists because they have laptop computers that they're carrying around with them. And they have certain approaches that they have. We collect evidence. That is, we look around us and see what we can see, and we gather this evidence, and we see from this evidence the relics of creation and the relics of the development of the universe after that point. And the next thing we do is we build special tools. And so I have to confess, I had the foresight to see that cosmology was a field that was ripe for development, but it took me 2 decades to build the tools and to get the procedures and to make it so it's possible to realize the thing we're doing. So sometimes it's easier to envision what you need to do than to actually do it. But if you stick to it, you can actually do that. So we developed a lot of tools and a lot of special procedures for how to take data and understand it. But once we had good quality data in hand, then we use computers to analyze that data. Then we make up models, and we run computer simulations and compare the models that we put in our computers to our observations and see what is the best description of the universe we observed around us. And you see, if you watch the CSI series, they do that in a more theatrical sort of way, but that's what they're doing. Okay. Now, today, this year is a special year, and this is actually very close to the 400th anniversary of the time Galileo built his own telescope and was the first person to point a telescope at the heavens. Before that, people were using naked eye observations. But Galileo we pull out, especially because it's 400 years ago, and because he also helped us develop the ideas of the laws of motion and the scientific method, the careful, rational thinking about observations and the world around us and applying that to what we see. It's not to say astronomy started with Galileo, because we know astronomy that all ancients were doing it. The Babylonians, there was a spectacular resurgence of astronomy under the Muslims 1,000 years ago, and Al-Mamun has actually 2 craters on the moon named after him. He founded the library and 2 observatories 1,000 years ago and started the collection of observations that led to this sort of thing. But it was Galileo followed by Newton, who showed that gave us the ideas we could describe nature with more than just observations and summing up the observations, but by actually making models that we could compare to the observations and save the phenomenon that we saw in very simple coding. And so Newton made his laws of motion, and he made the thing that we call the first universal law, Newton's universal law of gravitation, where he explained the motion of the moon, and then explained it to other planets, and eventually to the stars out in the universe. Now I'll show you another picture. The telescope you see over there, the telescope you see over here is a very simple, weak telescope. It was only a factor of 2 improvement. Galileo was able to make some astounding discoveries. He discovered 4 moons of Jupiter. He saw the phases of Venus. He saw the moon had craters. Just that extra bit of resolution did that. Now we build much greater tools in order to collect our evidence. So here's the Hubble Space Telescope, and here's a deep field picture from the Hubble Space Telescope. And can I have the lights down in the front some? In this picture, the thing that's remarkable about it is you can only see 4 stars. This is a star, this is a star, this is a star, and this is a star over here. Hopefully we can get the focus a little better too. And if you look, everything else in this picture is a galaxy. That is a collection of stars, and it's a very large collection of stars. This galaxy over here is a spiral galaxy. It's very much like the galaxy we live in. We think it has about 100 billion stars in it, just like our own galaxy. So when I look at this picture, I wonder, are there intelligent beings in that galaxy, wondering where the universe came from and how they can describe it? And are a few of them looking at our galaxy, studying our galaxy to see what we can understand? But if you look around, you'll see there are these galaxies, and some of them are yellow colored, like our sun. Those galaxies, it turns out, when you study them carefully, tend to be closer to us, and they tend to be more evolved. And it's not a surprise, the ones that are closer to us, you'll understand in a couple of minutes, the light is coming to them much later in the history of the universe than the ones that are very far away, because it takes light so long to travel. So the ones that you see behind it are smaller and more irregular. They're smaller because they're further away. They're smaller because they're younger and they haven't merged together, but they're yellow. They're not yellow. They're white and blue, which is surprising. It means their stars are burning much more fiercely in those early galaxies. and much more fiercely because we actually know the universe is expanding, which I'll tell you about. So the light should be shifted to the red. So the fact that there's still white and yellow. So from this picture alone, which you could go on and talk the whole talk on, you're able to understand a lot about the universe, and it's simply a matter of collecting good data and observing it and thinking about it carefully. That's the whole process. Now the next big step was taken as a result of the work of this man, Albert Einstein, who Time magazine named this person of the century. Undoubtedly, if they had existed earlier, they would have named Galileo or Newton the person of their century. And of course, we're looking for the person of this century because now we have great new discoveries, but we have great new unknowns that we need some genius or some new generation of scientists to help us solve. But the thing that Einstein did that was most impressive, that lets us think we can attack the problem of the universe as a whole, was he published a theory of the general theory of gravity, the general theory of relativity, and he published that in 1915. And in that, there's a lot of interesting things. The equations that say the curvature of space-time is set by the matter-energy content, and so putting matter in space-time tells space how to curve, and the curvature of space tells matter how to move. So anything that acts always has a reaction, and that happens. But the other thing is, as soon as you introduce curvature of space, you introduce a scale to space, and then as a result of that, you can have that scale change with time. That is, the universe can be expanding or contracting. And there were three people who found solutions to Einstein's problem: George Lemaitre, Alexander Friedman, and Wilhelm de Sitter. And George Lemaitre wrote an article, and then he wrote a letter to Einstein, enclosing the letter in the article, and mailed it to Einstein. And Einstein read it, and here's a picture of Lemaitre and Einstein at that epoch. So Lemaitre down here, Einstein on the top, and he said, "Your mathematics is correct, but your physics is abysmal, because everyone knows the stars are fixed in the sky. If you're a shepherd or a person who goes out and observes, every year you see the same set of stars progress across the sky. They're pretty much fixed night after night, and they just move slowly over the year, and they come back and start all over again." And in fact, the word planet, the word we use in English for the things in the solar system, means wanderer. That is something that moves relative to the stars. Every human knew that the night sky does not change except for very few things, and those are unusual objects. And so everyone knew the universe was static, and so the fact that the universe could be expanding and contracting, Einstein could not accept. He went and modified the general theory of relativity and added another term to it, and that ended up with another solution that also has the universe expanding, and that also got Einstein upset. And but later on, he reconciled. So there's a picture later on with Lemaitre and Einstein and Millikan, who did the oil drop experiments, and also the Sitter and Friedman, who found other solutions that had expanding and contracting universes, but mostly expanding universes. And they did that because the astronomer Edwin Hubble, after whom the space telescope is named, discovered that the universe is expanding. So, but before I get to that, I want to be very careful about one idea, and that's the idea about what the Big Bang means, because it's a lovely name, but it's misleading. Right? So here's a picture that was made by a former student of mine and his graduate student, and published. And this is the idea of how you can understand that it's not that here's space existing and then all the galaxies are clumped in the middle and they blew up and flew out. That turns out to be far from what's correct. But in fact, if the galaxies are already there, space itself is expanding between the galaxies. The galaxies themselves are not moving. And so space is three-dimensional, but to show it to you, I have to go to 2 dimensions. So we imagine that we're confined to the surface of a sphere, and that sphere has a certain scale factor, namely its radius. And you can look at it at different epochs. And so if you look, there are grid lines. Let me see if I can focus this. Well, I don't know if I can focus it. I should leave it alone until we see. It's slightly distorted. But there are grid lines, and if you will follow the grid lines, you will see this galaxy stays at the intersection, stays at the intersection, stays at the intersection, independent of the scale. That is, this galaxy, if it looks at the space around it, thinks it's not moving, right? It's just the space is expanding, But if it looks around it, it sees space at rest very close to it, and a little further out, the space is moving a little away from it. Further out, it's moving further away from it. Likewise, this galaxy is on a coordinate crossing and a coordinate crossing and a coordinate crossing, if you could see the focus a little better. And it is, in both cases, neither galaxy believes it's moving, because it's not moving relative to the space around it, yet the space is growing in between it. So this is not a case of objects flying out into pre-existing space, but space itself expanding. So it's not an explosion in the conventional sort of sense. Now you have to imagine this in 3 dimensions instead of 2, but that's, or an infinite plane instead of a spherical surface. Okay, so now to the discovery that reconciled it. Edwin Hubble was the astronomer who started studying what were called nebulae or clusters, and he was able to show that some of them were star clusters in our own galaxy, but many of them were too big and too far away to be in our own galaxy, but they were galaxies of their own selves. So he established the field of extragalactic astronomy. He started studying where they were, and after a little bit of more observations, he was able to show that the galaxies are moving apart from each other. Right? And so let me show you his first data, because this becomes the second universal law. His data is if you measure the distance to the galaxy and then measure the rate at which they're moving apart, and this is in kilometers per second, you can plot it up, and depending on whether you look at galaxies as individuals or as groups, you get 2 things that he drew, 2 lines that he drew. And he said there's a linear relationship. Well, you'll notice there's a couple galaxies moving towards us, but all the other galaxies are moving away from us. And the way you do that is you just look at a galaxy, and you see how big and bright it is, like this one, and you look at the absorption lines of calcium atoms in that galaxy, and you can measure whether those lines are where they are at the Earth or they're shifted. And if the universe is, if things are moving apart, there is effectively a Doppler shift. The wavelengths change. And so if you look at galaxies that are further and further away, you can see these lines move to the right. They get to longer wavelengths. So you can measure the apparent size and the apparent brightness, and that tells you an estimate of the distance. And you can measure the shifts in the wavelength, and that tells you the rate at which things are moving apart. And you find this is a linear relationship. This was the early data. Here's some somewhat later data, where now you're looking out to 1,000 million light years, or 1 billion light years, and you're looking out to velocities that are 20,000 kilometers per second, almost to 30,000 kilometers per second. You find this very nice straight line, this second universal law that tells us something about the universe as a whole. Okay, so George Gamow, who was a Russian who immigrated to the United States and was working on the issues of radioactivity and nuclei, and discovered that you could, if you had high enough energy reactions to overcome the electrostatic forces, you could actually have collisions inside of nuclei and change one nucleus and therefore one element into another. You could transmute the elements, which was the dream of the alchemist. But you could do that on a routine basis, provided you could get to a high enough energy and you could get up a high enough density to have collisions. And so he asked the question that I asked, where did all the elements come from? And he said, if there was a Big Bang, that would be the ideal place, because if you take the universe now and compress it by a very large amount, it'll be much denser, but if it was warm now, it'll be very hot when you compress it. And he said that will be just the things you need to have nuclear burning of primordial material to make things. And so he worked with his graduate student, Ralph Alpha, and they worked out the theory, and they determined that when they did the calculation, that 75% of the universe should be made out of hydrogen, and 25% should be made out of helium, and just a tiny smattering of other very light elements should exist, and that's all there should be. That's because there are no stable elements, stable nuclei, in the mass range from 5 to 8, and you couldn't get through that bottleneck. And at the time, he was arguing with Sir Fred Hoyle, who wanted to make the universe not in the Big Bang, but with a steady state, and he wanted to make the elements in the stars. And he graded the two of them on the quiz, and he said that he and Alpha got a 99% on the quiz because they could explain 99% of all the elements in the universe, maybe the hydrogen and the helium, and that Hoyle only got 1% because he could only explain the 1% of the universe, which happens to be carbon, nitrogen, oxygen, iron, the things that are in this room. Right? So it turns out we need both the Big Bang and we need stars in order to make what we see. And when he went to publish, he called up his friend Hans Bethe and asked him to be a co-author so they could have the alpha, beta, gamma paper. Those that know Greek know that's a science joke. So here's a picture of Gamow, Alfred Herman, and Fred Hoyle, who's grumpy for only getting 1%. But, you know, he was often in arguments. But one important part of their prediction that Alpha and Herman went through, calculated several times, was the temperature of the universe today should be around 5 degrees above absolute zero. This room is about 300 degrees above absolute zero. The sun is about 6,000 degrees above absolute zero. So 5 degrees above absolute zero is extremely cold. Right? But they predict that's the radiation that should be left over from the beginning of the universe. Okay, so there was no way to measure that, but 20 years later, in 1964, Bell Telephone Labs launched an experiment, which was called a Telstar satellite, and it was a test to see if it was possible to send radio signals to a satellite and have them relayed back to the ground. That was the idea. Was if you could do that, you could have communication satellites. We know that that was a successful experiment because we use communication satellites all the time. And as soon as it worked, they thought, we need to know how bright is the night sky behind it, because we have a certain weak signal coming from the satellite, and we have a certain noise coming from the sky, and if the signal-noise ratio has to be above 5 in order to have the error rate in the communications be sufficiently good. If the noise behind the sky is very high, this will not be economical because satellites couldn't produce very much. We need radio astronomers to measure the brightness of the night sky so we know whether we can proceed with this. So they hired 2 brand new PhDs, Arno Penzias, who's shown on the right in this picture, and Bob Wilson. Arno had been out for a year. Bob Wilson actually just graduated when they hired him, and they said, please come to Bell Labs and measure the temperature of the sky. And so they got there, and their boss started bugging him immediately, saying, what's the temperature of the sky? And the antenna already existed for Telstar, and a very good receiver already existed for Telstar. So they said, we'll make a measurement of the brightness of the night sky at 7 centimeter wavelength and get them off our back, and then we'll go make measurements at 21 centimeter wavelength, because we know there's hydrogen in the galaxy, and a map of the hydrogen in the galaxy would be a great thing to do. So they quickly made a measurement at 7 centimeters, and to their surprise, no matter where they looked, they saw a signal of 3 Kelvin, and they could show it was not coming from their equipment, because they had very good equipment, and they had a good reference load, and they could compare a 4 Kelvin reference load with liquid helium, which was rare in those days, to the 3 Kelvin from the sky, and know that there wasn't a mistake. And they even went and replaced part of the antenna to make sure it wasn't that. They did many tests and were able to show it wasn't coming from the equipment, it wasn't coming from the galaxy, it was coming from the sky. And then they ended up publishing the discovery, which they had got the Nobel Prize for 13 years later, which was the relic radiation, which was interpreted to be the relic radiation from the Big Bang. At least people hope that. And it took 14, 15 years before it was awarded, because people had to begin to establish that was what it was. And it was a milestone. I was a young student. I thought, that's great. It means the Big Bang is right and the steady state's not right, and these other models are not right. And I went back to my studies. But 2 years later, I went down the street from MIT to Harvard to hear a talk by a graduate student who was just graduating named Joe Silk. And there he extended and sharpened the question for me and told me this was actually an interesting problem. And the problem, he entitled his talk, Fluctuations in a Primordial Fireball. And the reason he did that was to point out what we now know. We didn't have good pictures like the one I showed you at those times, but there were galaxies, and galaxies had to form, and you had to have some model. If you're going to explain where the elements came from, you also have to explain where the galaxies come from. And so the problem with general relativity is it didn't know how to make galaxies, and it particularly had a problem if this radiation, this microwave radiation, was a relic radiation from the Big Bang. And it's a very simple problem. If I take you and I put you in the sun, what happens to you? You get burned to a crisp. Even worse than that, electrons are stripped from your atoms, and then the radiation pressure blows you, spreads you out like a big cloud. So you're better put together than a galaxy. You're more strongly bound together than a galaxy. So if I were to put a galaxy in something big enough to hold, a sun that was big enough to hold a galaxy, like the primordial fireball, the galaxy would be vaporized, and its atoms spread uniformly across space. And so if I go back instead of just a factor of 1,000 from the present time to 3,000 degrees, that's enough to do that. If I go back another factor of 1,000 times brighter than the sun, like a nuclear weapon, that's enough to completely ionize everything and spread the atoms absolutely uniformly everywhere. And if I go back another factor of 1,000, that breaks up the nuclei. That's the nucleosynthesis. So not only do you not have galaxies, but if this fireball, you have to go through in the right direction, build up first the nuclei, then you build up the atoms, and then you can build up the galaxies, and you have to have that. And so then the question is, how do you do that? And his answer is, you must have these fluctuations, and they must somehow have to survive through this fireball in some primitive form, and then you can start having galaxies form once the radiation releases the matter in order to make galaxies form. But as long as you're trapped in something as bright as the sun, you can't make a galaxy. It just gets blown apart. And so, to me, right, this says this is an important problem. Either this radiation doesn't come from the Big Bang, or it can let you see the beginning of the universe. To my colleagues, they're saying, this is a field that's not ready yet. This will never amount to anything. They're just guessing, right? And so it's just a difference in perspective. And you have to have a little better judgment than that. You have to see it's actually possible to build equipment in a shorter time tail in 20 years, because most people's careers don't last that long. Okay, so here's our primary tool. Our primary tool is that the universe is very big. So in this picture, the Earth is in the center. And if I look out to the sun, and I take a picture of light coming from the sun, I get an image of the sun as it was 8 minutes ago, because it takes light 8 minutes to get from the sun to the Earth, right? If I take the nearest 50 stars, on average it takes 10 years, right? Now if you take a photograph and you don't get the picture, it's only photographs that come in are 10 years ago, you're not as happy about that as having ones that come within a minute, right? Well, now with digital cameras you want it to come within a second or two, right? But that's not so bad. If I go out and I look at the Andromeda galaxy, which is down here, it takes light 2 million years to get to us, right? If you took a picture of the Earth 2 million years ago, there would be no lights, no electricity, there would be no people, no Great Wall, no temples, nothing, right? There was no humans on the Earth 2 million years ago. And so if you had an image of our galaxy or from 2 million years ago, you wouldn't see any evidence of humans at all, right? And of course, if you take a picture of our galaxy now, the Earth is so insignificant you don't see evidence of us, but if you could zoom in, you would. So just the size of space itself allows this. But now, if I go out to a typical galaxy, it could take, right, a billion years or many billion years. If you look as far as you can see, you can look 14 billion light years. You're looking back 14 billion years. You're looking back to when the universe was much smaller, therefore hotter. So eventually you can only look back until it's ionized, like the surface of the sun. You can see the surface of the sun, but you can't see inside of it. It's like looking to a cloud. The light scatters at the edge of the cloud, and you can't see into the cloud. And that's what the universe is. So in this picture, our plan would be look at different distances, look at spheres around us at different distances, get a sample of what the universe looks like, and plot that as at the distance divided by the speed of light, and that's the time that it is back in history. And you can start at the very early universe, right, when the universe is an embryo, and you can take pictures along the way, and you can see the development of the entire history of the universe. You can plot out like the life cycle of the universe. So that's our plan. And where are we? Well, I started working on the problem of making an image of this part of the universe, and we now have a very good image, and I hope at the end of the month we put up our 3rd generation satellite, and we'll make an extraordinarily good image of the beginning of the universe with extraordinary precision and many wavelengths so we understand it. And we've been making surveys of the nearby region, the galaxies that are relatively nearby, and if I rush, I will be able to show you pictures of the nearest, a sample of the nearest 1 million galaxies, and you can see where they are and what they look like. And so in between, we're starting to build up surveys to look at greater distances and different techniques for looking at different distances. So just to reiterate, here's the idea. We live here in the present in a spiral arm and a spiral galaxy about this location, sort of in the center of this sphere. If we look out further, we see around us in a volume relatively close by relatively mature galaxies. There's still some galaxies being born, but most of the galaxies have been around for quite some time, and they developed and matured quite a lot. If I look further out, I see the beginning galaxies, galaxies that are just forming. They have irregular shapes. Some are small. Many of them will merge together to make the more developed galaxies later on. And so this is, of course, schematic, because there are 100. That picture I showed you had only 2,000 galaxies in it. If I did tile the whole sky with pictures like that, I would see over 100 million galaxies. I would see more galaxies than there are stars in our own galaxy. Remember, there were only 4 stars in that picture, and there were 2,000 galaxies. And so modern galaxy, more developed galaxies around it, just beginning galaxies, and then you look out and you see the very embryo universe, and if you could look any further, you would see the very beginning of time, the very birth of the universe. And you can't quite see that. It's shrouded, just like you can't see the center of the sun. We can't quite see there yet, although there are other ways to try and probe that. The same way that you can take an acoustic picture, right? You can do an ultrasound of an embryo in the mother's womb. You can do an ultrasound of the universe and look at the sound waves, and that's what these speckles represent, sound waves that come to us from the beginning of the universe. So we actually are able to probe to a small fraction of a second, but it requires some interpretation of what we do. Okay. So this is the beginning of developing more sophisticated tools in order to make the measurement. It turns out we're trying to look at a signal which is the cosmic microwave background, which is 3 degrees above absolute zero, and this room is 300 degrees, so we're already down by a factor of 100, and we're going to try and measure that fairly precisely. And now we're going to look for tiny fluctuations in that. At the time we thought it would part in 1,000, so we'd have to get down to 10 to the minus 5 of the background. It turns out it was much lower than that, so we had to do better than a part in a million. So to measure the temperature of the sky over here to a part in a million, and temperature of the sky over here to a part in a million, and compare is difficult. So we do differences. We do a differential one where we look at this guy and this guy with 2 identical antennas and switch the receiver between them quickly and look for a difference. And then the antennas may not be identical, so you rotate it around. So this antenna looks at that side and this one looks at that side. And any change should be the change in the sky, and the equipment shouldn't change. But of course it might change if you rotate, so you do a double rotation. So that's the procedures. There's the hardware you have to build, and then the procedures you have to build. And I'm embarrassed to say, looking back, that it took 20 years to do this. But we had to put things higher, and we had to put them in space. So that's what it was. That's what I spent a lot of my life on. So this is one of the first ones we built after we did some on the ground. We built this. So this is a 1 centimeter wavelength pair of antennas that are looking at 2 different parts of the sky. And this is the 0.5 centimeter wavelength with the switch between it. So why do you do that? Well, the atmosphere is about 400 times as bright at a 0.5 centimeter as it is at 1 centimeter. So if you see a signal, you can prove it wasn't coming from the atmosphere, it was coming from the sky, because you can look at the ratios. And then you put this in a situation where it can rotate so that you can exchange the antennas. And then you cover it up so that radiation can only come in the horns. You don't want it leaking in some other way. And then you put it in a container, and you put it on an airplane. This is a picture of a U-2 airplane. Most of you guys don't know what this is, but this was a very famous airplane because it used to fly from Turkey to Scandinavia, and it would take pictures over the Soviet Union of the installations down below. It would fly very high and very stably and take very good photographs from very high. High so it couldn't be shot down, and very stably so that the images were very sharp. And so after one unfortunately landed in the Soviet Union and was a big disgrace to our president, that was released to be able to do Earth resources. And so all these things in the background are things that look down with optical and infrared sensors to look at the coastline, to look at forest fires, to look at crops, to look at other things like that. And there was one payload which is designed to look up at the sky. Everything else is looking down at the ground. And here's a picture of it getting ready to take off, and the graduate student, Mark Ornstein, who got his thesis on it. And here's the fit we made to the data we did with our observation. We saw the sky was 1 part in 1,000 warmer in this direction and varied smoothly to 1 part in 1,000 cooler in that direction. So already we're looking at 1/100th of the temperature of the Earth down to the 3 Kelvin, and then we're seeing at a part in 1,000 there's a variation, which we call a dipole, 1 warm pole, 1 cold pole. And we think we understand what this is due to. We thought we should understand what it should be to. It should simply due to our motion. If we're on the Earth we're moving because the Earth is rotating, the Earth is orbiting, and in the direction we're going, it should look warmer because we're running into the photons. In the direction we're leaving, it should look colder. The simple Doppler effect. So you can add up all the velocities that you have on the Earth. So this is where the satellite is orbiting in a polar orbit. But we're flying out of California. The Earth is rotating. The Earth is going around the Sun. And the Sun is going around the Earth. Newton told us all of this. So the solar system is going around the galaxy. And it's going in this direction. I'm going to have to switch lasers. The Sun's going in that direction. But the direction where we're seeing it's going was that direction. That was the surprise. We expected a signal at a part in 1,000 because that's roughly our speed around the galaxy. But we're going the wrong way. And that means the whole galaxy is actually moving. Right? The galaxy has to be moving almost twice as fast in that direction in order for our velocity to be subtracted to it and still leave us a vector in that direction. So we thought, how could that happen? Well, it could be the local group. We in Andromeda and several smaller galaxies are on a small group. They're orbiting around each other. Maybe that's. But you can measure the speed with which we're coming together, and it's only 80 kilometers per second. That means we're moving the center of mass at 40 kilometers per second. So that can't be the source. So what about the Hydra Centaurus supercluster and the Virgo supercluster? So this is a few thousand galaxies. This is over 10,000 galaxies. Well, that should be enough to pull us over. Well, when you do the numbers, it's not close. And there should be a tidal force that would be stretching the galaxies out. Not just our galaxy, but the group of galaxies we're in. So we had to make up the idea of a great attractor. And then the question came, how are these things distributed in the universe? And I'll show you a picture, I hope, of what that looks like. So we thought we had to go on with our next experiment. So we had to fly higher to get above more of the atmosphere. And we had to cool our receiver with liquid helium and to get it colder so it would have less noise. But we used the same trick. We had the antenna looking at this part of the sky, and then we'd have a mirror rotate in position so that it was looking at that part of the sky. So we're differencing two parts of the sky quickly, and then the whole equipment rotates. And you fly it underneath a balloon with a parachute and with a ladder to rotate against, and you go up and you make observations. So here's our equipment. The same thing, one antenna. Now it's cooled, liquid helium, and then a shield around it. A little thing to flip up so we can see it's working or not working. And then we made this map of the sky, and this is not a fit. This is the actual measurement of each little pixel in the sky. We had 3 balloon flights. We planned for 4, but our payload got lost in the jungles of Brazil, and it was lost for a little over a year. So it was slightly damaged, both by the rain for over a year and by the fact the person who found it tried to cut parts of it off with a machete and sell it in the market. That's how they discovered where it was. But you see it's warmer here by the part in 1,000, going to cooler here by part in 1,000. But you also see the noise of the receiver. But if you estimate how much comes from this signal and how much came from the noise of the receiver and ask how much was there left over, we could say there were no fluctuations at a part in 10,000. And that gets to be a problem because Joe Silk had told us that if we're going to make galaxies after the matter is released, the universe would be 1,000 times smaller. So that if the universe grows by a factor of 1,000, you needed seeds at a part in 1,000 in order for those galaxies to be left behind, and yet we're down to a part in 10,000. So this is beginning to be a crisis. So now the other experiments we're doing, which is to measure the spectrum to see if it's a black body form, they become more important because now we're trying to prove that it didn't come from the Big Bang. Well, we were trying to prove that. So we formed an Italian-American collaboration. We first did observations on White Mountain. So there's a 12 centimeter wavelength from Milano, 6 centimeter from Bologna, 3, 1, and 3 millimeters from Berkeley, and then Haverford College had an atmospheric thing. And then we had a liquid helium door in the ground, so we could look down at liquid helium or up at the sky and have a reference horn that pointed to the North Pole that would allow us to compare different parts of the sky and liquid helium versus the sky. So we went on to do that. That wasn't enough. We decided we'd take our equipment to the South Pole. So this is the Italian-American collaboration at the South Pole. This is the geographic South Pole, not the ceremonial South Pole. We're purists. This is just proof. That's me. Says George Smoot if we had enough resolution. I didn't have a gray beard yet then. That's frozen breath. But you see the horizon's very nice. It's very flat there. And this is, we had to move away from the South Pole where it was quieter. So we had a big ground screen, and we brought liquid helium because the South Pole wasn't cold enough. and then we had a screen against the wind, and we had a pit when the wind was blowing. We could bring our equipment down and work on it, even outside in bad weather. And but at the same time, we were planning the Cosmic Background Explorer experiment. So we have an instrument we're designing to have one antenna looking in the sky and one antenna looking at a 3 Kelvin load whose temperature we could adjust up and down until we saw zero difference between them. And then we would bring this device in, which is covered up, but it's a simulator of an almost perfect black body that we could then replace the universe with and adjust its temperature to make sure we still had a null and just read off the temperature at each of the wavelengths. And now the result of all those measurements is here, the part that's referred to as the black body form. You see the Penzias and Wilson's original point in red, the point that we measured on White Mountain and the South Pole shown in green, some balloon flights from the Princeton group, and then an experiment I'll tell you about later on that measured the anisotropy, 3 different frequencies. And then around the peak is the Phi-RAS measurement in red, and you can see how precisely it fits. And then about 6 months later, there was a University of British Columbia rocket experiment that was a small version of the Phi-RAS experiment that confirmed it in a much shorter flight. So you can see the noise. Well, you have precision over a wavelength range of a factor of 4 decades, right? So you're essentially going from 70 centimeters to less than 7/10 of a millimeter, right? You're measuring the shape, and the theory, the Big Bang theory, predicts this dotted line. Only the temperature has to be slightly adjusted, but the shape is extremely precisely shown. So now we have the full crisis. This is truly a relic radiation from the Big Bang. This is now late 1989 and 1990. Now we truly have this relic radiation from the Big Bang, and so far the fluctuations we're seeing are below 10 apart in 10,000, and that's a conflict. We can't make galaxies in the Big Bang theory. There again to be papers appearing in the literature saying the Big Bang theory is wrong because it can't make galaxies. And there turned out to be 2 solutions. First of all, we had to get the Cosmic Background Explorer continue taking data. This was the artist concept of what it would be like from the 1970s. There were 2 experiments inside the liquid helium door. The first one was the spectrum measurement. The second one was designed to look at the first light, that is the light from the first generation of stars and galaxies. And that's called, I'll show you the data. And then there were the experiment that I was responsible for, the differential microradiometers. And we were all co-experimenters in all the experiments. So it was a true team effort. Okay, so here's the picture of the whole sky done by the diffuse infrared background experiment. And this was the first very good evidence we have that we live in a spiral galaxy. We're in it. You can see the galactic center and the galactic bulge and the galactic plane. So we're in galactic coordinates. And you see a little fuzzy stuff in here, which is dust and gas clouds in the plane of the galaxy. And you see a few stars off the plane of the galaxy. Though we're in the galaxy, we're almost vertically in the galaxy, but we're far out from the center. So even around us there are stars, so there are a few stars you see no matter which direction you look, roughly. But there's plenty of place to look between the stars. And when you do, you start seeing that there's extra light coming from the universe. And that light is the light that's coming from first generation of stars and galaxies. And if Hoyle is correct, we would think that essentially every time you burn a hydrogen or helium into a Hoyle element for each nuclei you had, you should get 1 photon. So just counting the photons should tell us if Hoyle should get his 1% or not, right? And the answer is he should. In fact, when we did the counting, we were getting twice as much as we had predicted. Now, there turned out to be a reason for that, and I'll show you in just a second. But it's because some of the stars started earlier than we had thought, and they were able to burn and make other elements, and that made the dust and the gas clouds you were seeing before. And some of them absorbed the original starlight and re-radiate it in the infrared there, but now the expansion of the universe has shifted into the far infrared. And when it takes a photon and re-radiates it to the lower color, it produces 2 or 3 photons, and so you get 2 or 3 for 1 for sale. So the fact you see twice as many, you have to count the energy and then see that it comes out that is roughly correct, that roughly 1% of the matter in the universe has been burned into heavier elements. So there was another survey since then called the 2-mass survey, and in this picture, it's the first mass picture that I'm showing you. There are over 1/2 billion stars shown. You need a high-resolution screen to see it. Even my screen doesn't quite do it. This is kind of poor. You can see some extragalactic objects, the large and the small magnetic clouds here, but you see the plane of the galaxy, you see the dust in the galaxy and the bulge, and you see many more stars, but you can do the same thing we did before. Instead of blanking out the stars, you can average over the stars here and subtract them from the Derby map, and you still see that roughly factor 2 more photons than we expected, but the right amount of energy that we expected for Hoyle to be right in making the heavier elements in the stars. Okay, so here's a picture of the Cobe Satellite the last time that I saw it. I had to go and inspect it because it launched from the West Coast, and I live on the West Coast of the United States. And you see the doer with a cover over it, because you can't leave it in the air, it will freeze the air around it, and you have to blow the cover in orbit. And then you see the differential microwave radiometers that we had to cool in order to get an extra factor of 2 sensitivity, because we were needing that because the limits were getting tighter and tighter from our balloon observations and so forth. And this is a picture of what the satellite looked like in orbit. So it goes into polar orbit, and you try and make it orbit on the Earth, around the Earth on the day-night line, so that the satellite can be looking with the Earth directly below it and the sun at 90 degrees. You tip it slightly back so that everything inside the shield is in the shade, and then you rotate it to keep it uniform like a chicken on a rotisserie, and you have the solar cells, and that way you scan these circles on the sky. The orbit scans those circles around, so you cover half the sky each day, orbit 14 times a day, and then as the Earth moves around the sun, you sweep out a whole mixture of the sky, a whole map of the sky. And so here are the maps we made. The first map would be very uniform, so I don't show it to you. The sky is extremely uniform. Here you see the dipole, but now in galactic coordinates. So here's the hottest spot to the coolest spot. Now this is the true data. Now the noise is negligible. You can see what the sky really looks like. And now you also see the galactic plane, where you can get a proposal in to discover new continents. We got a pretty good map. Now, though, we want to understand how the continents form, what the force is shaping it, and what are the details and how they're going to evolve, and how is the climate going to change. So you have a certain area where you've actually made enough progress that you can actually define good questions. And so the other advice I give to young researchers is pick an important question, but an important question you could get done in 5 years, right? Because you've got to move on with your career, right? And if you think it'll take 5 years, it'll probably take 10, or in my case, 20 years. And you want to get it done, you know, in a timely way. Not that I didn't do other things along the way, but you have to be able to choose problems that are not only important, but that you get done. And so I don't know. I can spend my time helping to get a dark energy mission going, because my career is fairly well established, and it will only be hurt some if it fails or takes 10 extra years, right? But it's a really important and challenging question, but it may take 100 years to understand what dark energy is, or to find another theory of gravity. But the dark matter is something you can go after. Clearly the cosmic microwave background was coming right. The technologies were coming together. There were newer and better electronics and radio receivers. There was the opportunities to go higher and to go into space. And there were new techniques that you can do, and computers coming along to analyze it. There are new areas that are opening up. We can use gravitational lensing to the fact that something that Einstein thought would never be observed now is going to be a routine tool. We can look at light from very distant quasars and galaxies and see how that light is bent by the intervening material, including the light from the cosmic microwave background, the beginning of the universe. We can see how it's slightly distorted by the fact that space is distorted, and that'll tell us about the intervening matter and energy. And you can also use it to learn things about the trajectory of the universe. So not only do we study the trajectory of the universe as a whole, but we can study how structure grows, and we can study how matter is distributed. Those are tools that we didn't have 20 years ago, and we have now. So that there are opportunities, but they are tools that require good mathematics and tremendous computer systems, and those are available now, and we can do those kind of experiments. So there's lots of interesting challenge. So my advice to young researchers is, I have a list of 8 questions. Any one of them are important. Pick out the one you like the best and you think you can get done in 5 years, and team up with people and do it. Science is now a worldwide effort. You know, I've got collaborators in the United States, in Europe, and now in South Korea. This is a pen for Ewha University, Ewha Women's University in South Korea. We have collaborators there. We're going to be looking for collaborators from all around. I have a student working in my group from Singapore, right? It's just down the street. And, you know, we need the brain power, and we need the excitement, and it's a worldwide effort because it's your heritage too. It's everyone's heritage. We all came from the Big Bang. We all live on the Earth. We want to know how the world got created. That is, how the universe got created, how the galaxy got created, and how the Earth got created. We also want to know how to save the Earth, right? We're having a tremendous impact on it.
Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh.
I'm sorry, what was your name? Don't be shy, just tell me.
You are welcome. You are welcome.
Pleased to meet you.
One of the Islamic countries. My name is Muhammad Toba Saeed. I am working as a lecturer in Islamic Studies at the Faculty of Islamic Studies at Johor. I hope to ask you some questions. I understand from your talking the universe is expanding. Universe is expanding, and the scientists discovered that at 20th century. But we know that already in 7th century, because we have in the Holy Quran one verse. أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم والسماء بنيناها بأيد وإنا لموسعون. The meaning is Allah has created the universe and the universe is expanding. My question is, if the universe is expanding, one day will bomb or not? Yani it will has end or not? And from what the universe is created? From what material the universe is created? Because we have in the Holy Quran, the universe is created from material same like smoke. Material same like smoke. This and also I want to ask, which is moving faster, the sun or the moon, which is moving sun? Because we have in the Holy Quran one verse also is talking about that the moon is moving faster than the sun. That's all. Thank you very much.
Okay, so there's many questions there. And so let me start with the easy one about what's moving faster, the sun or the moon. And so what we learned in physics is as long as we have simple things like conservation of momentum and energy, they are telling us something about the properties of space and time. And that tells us as long as those are conserved, that all motion is relative. There's no absolute standard of reference. There is a frame in which the expansion of the universe looks particularly simple, just like there's a frame in which the motion of the Earth around the sun looks particularly simple, right? So the question about which is moving faster, the sun or the moon, is it's a question of where you choose to observe from, right? You can do it from on the Earth, or you can do it from on the sun. If you're on the sun, the sun is not moving at all, right? And the moon is moving fast. If you're on the Earth, the moon is going around, right? But the sun is going around, and the sun is further away, and it's going faster. But that's a question of you have to finish defining the frame, right? So there's the other question about what's the universe made out of, and so forth. I thought you were going to ask me a religious question about if there's a contradiction between religion and studying cosmology and the birth of the universe, because clearly in most religions like Christianity and Islam, the God is Allah is the creator of the universe, and I think that could easily be true, and that in fact studying the universe is studying God's creation, and the nice thing is it's another form of the writing of God to see the universe, right, in terms of what's happening. And we don't know the answer to which the universe came from. There's several different theories about the beginning of the universe. One of them, the universe comes from nothing. It's not only small, it's absolutely nothing. And in the case that the universe happens to be perfectly flat, and therefore now effectively infinite, although there's There used to be geometry and destiny. The dark energy kind of provides a little fuzzy area in there. In that situation, the total energy of the universe is zero. That's like saying the total cost of my house is zero, because I found a lender that would lend me 100%. This is a bad thing to bring up these days. That I found a lender that would loan me 100% the cost of my house. So I borrowed the money and I bought the house, and my net worth is zero. I owe, $100,000 to the lender, and I have a house worth $100,000. And that was fine as long as the value of the house went up. But when the value of the house went down, that wasn't so good, right? And it became part of the world economic crisis. But in the case of the universe, the bookkeeping is much better. And in the case of the universe, we know we're very close to a zero net energy case. That the beginning of the universe came from a very small amount of material, and people have done calculations, including Alan Guth, who was one of the inventors of inflation, that had you had sufficient resources and energy with simply 10 kilograms of material, you could produce a baby universe that would grow and become as big as our universe. Now, I have confidence that if you had a lot more time and a lot more intellectual power, the way Allah would have, you could do it for less. Right? The universe would be a bargain, and not only that, I could answer the question, and had I had more time and I was hoping what someone would ask, I could answer the question, why are there 100 billion galaxies when one would have been enough for mankind? And the answer is, if you say the laws of physics are the laws of God, then you say quantum mechanics tells you that when you start off with a very tiny universe, quantum mechanics is very important, and there must be quantum mechanical fluctuations. But when I went through the accelerating expansion of the universe called inflation, and then the continuing expansion of the universe, things grew by 60 orders of magnitude, and things that were smaller than an atom got to be bigger than our galaxy. So our galaxy was once a quantum mechanical fluctuation, so is that common cluster of galaxies, and so is the Great Wall. They were once quantum mechanical fluctuations. They were microscopically small in physical size, but they got stretched to astronomical sizes, and that when you go into a very tiny region, which the universe was made from, was very dense, but very tiny, and you're going to have hundreds of millions of quantum mechanical fluctuations, therefore you will get hundreds of millions of galaxies, and there's nothing you can do to stop that unless you can violate the laws of quantum mechanics. Right? And so it's a very beautiful picture. It's very economical in many ways, but it has all these strange new elements in it, right? That you know you must have, and it's kind of the universe exposing itself to us and saying, here's another veil, here's another mystery for you to explore. And so for me, it's very exciting to learn about this.
My name is Selma. I'm a PhD student in Brunei in Dar es Salaam. I have a very short...
Closer to the microphone. I heard your name is Selma.
Selma, yes. I would like to ask a very short question. What is the purpose of a dust as a matter in the universe? Thank you.
So the question is, what is the purpose of the dust? And of the which?
As a substance, as a matter, energy matter in the universe.
All of it, or just the dust?
Just the dust.
All right. So this is the question about why did God make flies, kind of thing. No, the dust is an automatic consequence of producing stars and having the stars burn the primordial elements from the Big Bang, the way Gamow and Alfred Herman calculated. You have this primordial material, stars form, they do nuclear burning, fusion, and they produce the heavier elements, and then the stellar winds take those elements out, or supernova take those elements out, and they turn them into huge clouds of gas and dust. And the dust will coalesce more quickly because it can radiate electromagnetically better. And a lot of the dust is made of carbon and water, carbon molecules that make these carbon fibers, and water molecules that form together, and they freeze, and they make sort of dirty dust particles, carbon nanotubes kind of materials. And it's a very effective radiator, both because of the particular atoms, but because you get a larger structure, you get a more complicated. So they actually cool more quickly, and they make clouds, and those clouds then actually help the next formation of solar systems after that. But it's not I don't know if that's a part of a plan or whether that's just a byproduct of the plan that when you burn, wood for heat, you end up getting ashes, right? You're burning nuclear elements, and some of the ashes you get are dust. That dust turns out to make dust clouds. It also turns out to eventually make planets and in places where you get life. But many of those dust clouds have a lot of interesting molecules in them too. So many molecules have been discovered by radio astronomers in space, and they're good radiators, and you see molecules. You see, I think several, almost most of the amino acids have actually been shown to exist in molecular clouds in space, right? So they're molecular dust clouds, and so there's a lot of active chemistry. That's the wonderful thing about cosmology is you've got to know particle physics and nuclear physics. You have to know everything. It's fun. It recapitulates all that we've learned in science. So thank you for the question, and thank you all.
In the context of the work of bridges, which is trying to bridge various gaps to establish peace. And if you look at the last few pictures on the screen that was shown to us, the billions of galaxies swirling around in space, and the galaxy in which we are in is only just one of them. And we are a planet, I don't know, one body among how many millions within our own galaxy. And within our planet, there are so many countries at conflict with one another. And then if you translate that to individuals, ourselves at conflict with so many others around us as well, that shows how the significance of it all. And if you look at that, there's no reason for us to be quarreling among ourselves as individuals, nations among nations, because we are so minute in the total concept. I thought that was the message that I get out of all this. Now, once again, Your Royal Highnesses, ladies and gentlemen, can we show our appreciation to the speaker?
Tagore says, where the mind is without fear and the head is held high, where knowledge is free, where the world has not been broken up into fragments, where words come out from the depth of truth into that heaven, let my country awake. I would now like to invite Yang Berbahagia Tan Sri Samsudin Osman, President of Perbadanan Putrajaya, on behalf of Perbadanan Putrajaya and the Perdana Leadership Foundation, to present gifts of appreciation to His Royal Highness the Crown Prince of Perak Darul Rizwan, Raja Nazrin Shah, as the Malaysian Honorary Chairman of Bridges. Dipersilakan. Yang Berbahagia Tan Sri would also be presenting token of appreciation to Yang Berbahagia Tun Dr. Siti Hasmah Haji Muhammad Ali. And a gift goes as well to Mr. Uwe Morawetz, Chairman of the International Peace Foundation. Tan Sri, if you could do the honors, please, to Mr. Uwe Morawetz, Chairman of the International Peace Foundation. Thank you, Tan Sri. I'd now like to invite Yang Berbahagia Datuk Sharif Shamsuddin, Honorary Treasurer, Perdana Leadership Foundation, to present tokens of appreciation on behalf of Perbadanan Putrajaya and Perdana Leadership Foundation to Professor George F. Smoot, 2006 Nobel Laureate in Physics. And not forgetting our able moderator for today, Yang Berbahagia Tan Sri Dato' Dr. Omar Abdul Rahman, President and CEO of Malaysia University of Science and Technology, MUST. Thank you, Yang Berbahagia Dato'.